Now, if you remember, so I assume that all of you can see the screen with chapter 8, cosmology. And if you can't, then please let me know. Right. Right. So if I go back to the note, just to remind you what we have done up to now. So we started this chapter defining what is cosmology means. So that is the nature, evolution, and the origin of the universe. So that's basically about the studying of nature, evolution, and the origin of the universe. And then we discussed some of the key observed properties of the universe. If you go and observe the universe, what you can see, right? And under that, we talked about Kolber's paradox under dark night sky, and then discussed about cosmological principle, which is very important for the mathematical formulation that we have been discussing up to now. And then the Hubble's law, which basically explains about the expansion of the universe. And then the cosmic microwave background radiation, right? So cosmic microwave background radiation is important for us in two ways. I mean, it's important in a lot of other ways as well, but in this section, we discuss basically about two ways. The first thing is to get an idea about this isotropy and homogeneity of the universe. And also, it's one of the strong evidence for the Big Bang theory, right? So we discuss all these things, and then the evidences for the isotropy and homogeneity, and then a little bit about the cosmic microwave background radiation and the Hubble's law. And I explained to you how you can get this relationship using the redshift relation for small redshift galaxies, and what exactly Hubble did to get this relationship. And then we talked about Hubble law, and then discussed very briefly about what this expansion means. And then we went on to talk about the Robertson-Walker space-time, right? And this is related to that the general theory of relativity section, especially for the mathematical part. So the idea is we now know that we can assume that our universe is isotropic and homogeneous, and then we need to find a metric that define these qualities of the universe. And then this is the metric that we are going to use for that. So this is called Robertson-Walker space metric. And then we actually discuss some of these terms in the metric and some of the properties. And then what happens in cosmic timing, I mean, when you have an expansion of the space, what happens? And we remember that I told you that it's basically the expansion of this grid itself. However, the coordinates will remain the same, right? And these are called, co-moving coordinates. And then I discussed about the curvature parameter that is in that Robertson-Walker metric, and also expanding and contract, how the expanding and contracting universe is related with the scale factor that you can see here in this Robertson-Walker metric right here, right? So that's a time dependence term. And then I talk with you about these curvature parameters in the Robertson-Walker metric last time. And remember that we talked about the three options that represent in this particular metric based on the value of K. If K equals 0, then we used to tell that it is a flat universe. And if K equal +1, that will be a positively curved universe. And for K equal -1, that will be a negatively curved universe, right? And there is so this was not in your note in the previous time, so I added a diagram so that you can have a general idea what these three curvatures actually means, right? So the positively curved means is if you take an internal angles of a triangle, for the positively curved one, the angles will be greater than 180, right? In normal Euclidean space, we know that for a triangle, if you add these three internal angles, it should be 180 degrees, right? So that is this K equals 0 flat space. Yeah, you have all this Euclidean geometry and everything. However, that doesn't valid for curved surfaces. And the two other options for the curved surfaces are K equal -1, which is the negatively curved space. So which has a shape something like this. And the addition of the three angles will be less than 180 in that case. Now for a positively curved space, these three angles, if you add up, that will be greater than 180, right? So that is kind of, the properties of these different curved space and how you can understand and get an idea about these curvatures, right? So we only have these three curvatures because those are three values that the K can get due to the fact that we are assuming an isotropic and homogeneous universe, right? So which means if it is curved, the curvature will be same everywhere. Right. Now let's look at how to find an expression for the proper distance using this Robertson-Walker metric, right? I think we did that. I think we have defined what proper distance in previous chapters as well. And proper distance is basically the distance measured with the moving observer, right? In the observer's frame. And if you take a time t for an observer and he is trying to determine the distance sigma to a galaxy along radial coordinates, that means your angular coordinate both theta and phi should be constant, right? And so once again, what this observer is trying to do is at a particular time called t, he or she is trying to determine the distance to a galaxy in his frame, and that distance is sigma, which is the proper distance. And assuming that he is measuring things along radial coordinate, which means that theta and phi should be constant, right? So we do it in this way because it will make things simpler. So what that means is for a particular time t, then dt will be equal to 0. And then you are not changing theta and phi. So d theta and d phi will be also equal to 0, right? Now, if you go back to the equation 4, which is this equation right here, basically the Robertson-Walker metric, and from the previous chapters, you know that this ds squared is kind of, the line element right here, which you can write in this way directly as d sigma. And then, so if you can't remember this, then just go back and look at, the previous chapters, right? So I have mentioned it before. And your equation will become something like this, because for a time t, the dt factor will be 0. And then if you go back here is this part. So the dt will be 0. So all you have is this section right here, r squared t times this whole expression. And in that also, when you take a constant theta, these two terms, d theta and d phi, will vanish, right? So what you will have is only this first term that depends on the r. And if I go back to the equation, and that's what I have mentioned here at the end, you will have d sigma equal rt times dr squared over 1 minus kr squared. There's a plus sign here, which should not be there. So let me correction. Right. Now, if you, for this equation, if you take r to be equal to this variable called chi, and this is actually assuming that you are measuring a distance from an origin to a certain point, right? So that point will be, let's say, 0 to chi, like that. So if that is the case, then you have to integrate it, this dr, from 0 to chi, right? So what you have to do is, now you have to do an integration here, and this r, capital R, is the scaling factor that depends on time only. So it is a constant when you are integrating with respect to r, right? So what you would have is, if you do the integration and see, here is this curvature parameter k. Now this k can have three values that can be +1, 0, or -1, as I have pointed out earlier. So there should be three cases here, right, for three values. And so you have to integrate this expression for k equal 1 first. So that will give you 1 over 1 minus kr squared and the square root of that. And all of you know that that is, if you integrate it, the answer should be sine inverse r, right? And then you have to, that is when k is equal to 1. And then you have to substitute the limits. So the 0 limit will become 0. And then once you substitute the other end, what you will get is this expression right here for the proper distance. Okay, equal +1. So that is for the positively curved space. And for the flat space, k equals 0. Then if the k equals 0, this term will be equal to 0. So straight away you will get just RT here times whatever the variable. So that is chi. Right? I mean, just go through yourself, you can easily understand this. And the other option is for the negatively curved space. If you do the integration, this will be 1 plus kr squared, and that will give you a hyperbolic function like sine sinh, the inverse of hyperbolic sine, right? That is what I have mentioned here. And right, so those are the equations that we have. And if you plot these, and so if you look at the book, you will see the same thing. And if you plot these functions with the x-axis with this co-moving radial coordinate, that is chi, in this these three expressions, and the y-axis as the proper distance, sigma over RT, so sigma divided by the scaling factor, right? And so here are the three graphs, and what you can see here is up to a certain value, all three options looks like the same, right? So it is, you know, when this co-moving radial coordinate, you know, exceed the value of 0.4, something like that, and that is where you can see the difference, right? So for the, and even when you go for up to 1, the sine inverse x will stop right here, right there. So it will not exceed beyond that, and the other two will exceed, right? And that's what happened for these three options, like for three curvatures of the universe, right? Now, actually, there is not much use of looking at this co-moving radial coordinate chi. What happened to that? So what is, for the proper distance, because practically you cannot measure it, right, for the proper distance. And so what is important for us is how this proper distance change over the time, right? To look at that, we are going to use differentiate the proper distance with respect to time in this way. And that is for the, so remember that we have this equation, the first equation, equation number 8. So you can differentiate that with respect to time. Then the time dependent component is the scale factor, right? So you get d sigma over dt. So that will be equal to dr over dt times sine inverse x, sine inverse chi. And that's what I have written here. And for all three options, you can do the same thing for the equation 12. So that is this equation right here. You again differentiate with respect to time. So what you get is d sigma over dr. So that will be equal to chi again. That is for the flat space, k equals 0. And you will get a similar type of equation here as well, right? So those are the three equations that I have written here, right? So just take 8, 9, 10, these three equations, and differentiate each equation with respect to time to get these three equations. And now again, you can actually substitute for these sine inverse chi, and for this one and this one, using the equations 8, 9, and 10. Because from here you can take an expression for the sine inverse x. So that sine inverse chi, so that will be equal to sigma over r. And here also the chi will be equal to sigma over r. And here sine hyperbolic sine inverse chi will be equal to sigma over r. And you can see that all three possibilities will give you the same expression for sine, not the same expression, but the sine inverse chi and hyperbolic sine inverse x chi, and that is written right here. So which means you can now take each of these expressions and plug those in these three equations in 11, 12, and 13, right? So for the sine inverse chi, you can plug sigma over r right here, and that will give you this equation number 17. You can see that in the left hand side you have the d sigma over dt, and then you have d sigma over dt right here. And then on the right hand side you have dr over dt. So that is right here. And then you have sine inverse x right here. Now this sine inverse x is equal to sigma over r. And so for a reason I have written r right here, and then the sigma after dr over dt, right? Now if you look at carefully, all these three equations will lead to the same expression, right? So that's why I have not written here three expressions, because all those three equations will give you the same expression, which is this expression, equation number 17. Like for example, here d sigma over dt and dr over dt, and you need to plug the value of chi. So that is sigma over r, right? And here also for this one also you have to plug sigma over r, because all three values are same here. And that will lead you to just one equation, that is this equation right here, right? Now you can write this particular equation in another way. And the standard way of writing this is, for the d sigma over dt, that is the proper radial velocity. So that's how we define it. And we normally define it as Vp. And this term 1 over r dr over dt is considered as the Hubble parameter, right? Now remember that this particular term is very important, and I would highly recommend that you remember this equation for the Hubble parameter ht, right? And you can see that it is not the Hubble constant, by the way. It is something similar to that, but we call this as the Hubble parameter because it's a time dependent function, right? And then the dp is right here, is the proper distance, right? So that is sigma, right? Here sigma is the proper distance. Now we have just changed the variable here, but it is still the same proper distance, right? Now this relationship looks like it's pretty much similar to the Hubble law, but I will show you what are the differences with this expression compared to the Hubble law. And this particular expression that I have given from equation number 18 is known as the velocity excuse me, velocity distance law. right? And Vp is the proper radial velocity, and dp is the proper distance. And this term right here, ht, is what we call as the Hubble parameter. And I have again defined it right here. That is 1 over r, dr over dt. And that quantity ht is known as the Hubble parameter, right? So make sure that you remember this equation, because that particular equation is important in many ways when you apply and look at different models of the universe, right? So it is always nice to remember these type of relations so that you can directly use it. Now, what this velocity distance law means is that if you consider a fundamental observer is moving away from every other fundamental observer with the proper radial velocity, that is proportional to the distance that separates them. Right? So I guess you can read through and understand it. And now this relationship, which is given in equation number 18, is actually derived using the Robertson-Walker metric, right? So that's what we have done. However, this has some kind of similarity and also differences when you compare this with the Hubble's law, right? So that is what is important here. Now, if you look at the Hubble's law, and this is the Hubble law that I have defined earlier, right? So it is also velocity, which is measured using this redshift velocity redshift relationship, and then that should be equal to h naught times t, right? Now this is actually an observational relationship, right? Because what Hubble did was he measured the distances to each and every galaxy that is nearby, and then take the spectrums and look at the spectrum to find the redshift, which he can convert it to a velocity, right? Then he plot all these things in the graph where his x-axis was the distance and the y-axis was the velocity or the speed, right? Then he got this nice linear relationship, and the gradient of that graph was what we called as the Hubble constant, right? Actually, this Hubble constant presents the current value of the Hubble parameter. So that is the relation between those two, right? Now, the one thing is Hubble law is an observational relationship only valid for small redshift, which means this Hubble constant would not be a constant if you go for very high redshift values. However, for smaller redshift that we are considering, we can still take that as a constant, and it is an observational relationship. The other thing is, if you want to, combine or convert this Hubble parameter into Hubble constant, the idea is actually Hubble constant is the present value of the Hubble function or the HT or the Hubble parameter. Right? Hubble parameter is, it's a function of time. And if you put the time as the present time, that is t equals 0, then you will get the Hubble constant, right? So that is the relation between those two. So you should actually remember the Hubble's law, and at the same time, it is very important that you remember this expression for the Hubble parameter as well. Right. Now this Hubble parameter leads to some interesting discussion here. That is, if you look at this equation 18, that is this velocity distance law, that from that equation 18, you can see that you have the Hubble parameter and distance on the right-hand side. You can set the distance in that particular equation and the velocity. Let's say velocity is the velocity of light. Then we call this particular distance as the Hubble length. So that's a specific name, right? If we set the velocity as c, then what you would get is, with the current Hubble constant h naught, the distance that you get, we normally call that as a Hubble length, right? So the idea is, if you look at a galaxy at that amount of distance, dh, so that particular galaxy will be receding from us with the speed of light, right? So that is the idea. I guess you can understand it. The c means the velocity of light. I guess it's better to keep it simple. So let me just have it simple. Right. So I hope every one of you got the idea, right? So you have this relationship, velocity distance relationship, and if you set the velocity as the velocity of light there, and then with the current Hubble constant, if you calculate the distance of that particular galaxy which is moving away from us with the velocity of light, then that distance that you are going to calculate is known as the Hubble length, right? So what this means is, if you have a galaxy that is further away from this Hubble length, which is the particular distance that a galaxy could move at a speed of light, right? Or moving away from at the speed of light. So if you have a galaxy that is even far away from that distance, which is this Hubble length dh, then those galaxies will move away from us at superluminal speeds. Right now, this particular term, superluminal speeds, means velocity is exceeding the speed of light. Right. So that's maybe this is the first time that you meet this particular term. Make sure that you understand what that means. Right. So that means the velocity is exceeding the speed of light. Now, we have been talking up now about all the velocities up to the velocity of light, right? So you cannot talk anything beyond that velocity of light. But here it seems to us that it looks like it is possible, right? That having a galaxies that are moving away from us greater than the speed of light, right? Now I have an exercise right here, even though I haven't told you directly. Find the current Hubble distance in terms of megaparsecs. Assume that the Hubble constant is 70.4 kilometers per second per megaparsec, right? Now, can one of you try this? Oh, please, everyone try this one and give me the answer for this one. So I have given the Hubble constant, which is kilometers per second per megaparsec, and the velocity of light is, let's say, 3 times 10 to the power of 5 kilometers per second. So you have the two numbers. What I want from you is the Hubble distance, so Hubble length. So you have the equation right here as well. So calculate the Hubble length in terms of megaparsecs, and then let me know. You can post it to the chat window, right? So I will give you a few minutes for that. I have answers only from 2 of you. How about the others? So I'm waiting for them. Right, 3 is here. Right, so I got the answers from most of you. Right, almost all of your answers seems to be correct, but let me give you a rough answer for everyone. So that will be around 4,200 megaparsecs. Yeah, 4,200 megaparsecs. So this is an approximate value, but all of your answers, 4,261 or 60, something like that. So that's what all of you have, but seems to be all the answers are correct. And the value is 4,200 megaparsecs. And so what can you learn from here? It is that the galaxies that are 4,200 megaparsecs, more than 4,200 megaparsecs away from us, they are actually traveling at a speed greater than speed of light, right? So which means, so that is the Hubble distance, 4,200 megaparsecs. Now, if you actually convert this into light years, that will be around 13.7 billion light years, right? That is interesting, and this is roughly the age of the universe, right? Not the exact value, but very close to that. But in this way, you can actually, if you need, you can convert, get a rough estimate for the age of the universe as well. And what we believe now is this Big Bang happens around 13.7 billion years ago, right? Now, if you started to read the assignment that I have asked to read in that last chapter of that book, or the chapter 29, you probably will understand this, right? So that particular chapter is combined with what we are what I am teaching here, and this is the method, kind of the mathematical background. But that particular chapter that I asked you to read is kind of giving you the whole picture as it discuss some of these expansions, Hubble law, expansion of the universe, dark matter, dark energy, those kind of things, plus the Big Bang together. So once you have this knowledge, well, once you are learning about this, it is easy to understand that chapter, right? So that's why I assign that to you. And also that is make sure that that's kind of, the last chapter of your syllabus, right? And right, now the next question that you probably have is like, whether this is allowed, because we should tell that even in the special theory of relativity, these superluminal speeds, it is something prohibited, or you cannot even talk about those things, right? But here there is something that you to note here. It is important to note that the special relativity prohibits superluminal speeds in an observer's inertial reference frame, right? So that is what is important. But galaxies moving away from us at a superluminal speeds because the space itself is expanding, right? So those are two different things that you have to understand, right? It's not like something is moving away from us. It is the space itself expanding. Because of the space expansion of the space, those galaxies are moving away from us. Those galaxies are on this space now. So that's what actually happens, right? Right. And so I have put a problem here. However, assume that the recessional velocity of two galaxies moving away from each other has been constant since the expansion of the universe started. So that means since the beginning of the universe, place where this expansion started, we assume that recessional velocities of two galaxies moving away from each other has been a constant since then, right? Now, assuming, making that assumption, I am asking you to find the elapsed time since the galaxies were in contact. Because if we think about these two galaxies before the expansion, they should be in contact with each other. No? So it is when the expansion started and when the space get started to expand. So that is where these galaxies started to move away from each other, right? Now the question, what question is asking from that particular point, what is the elapsed time? How much or how long or how the time that we have spent since that particular point, right? So I hope you can understand what I am telling here, and yeah, that is basically the age of the universe, right? And so I want you to do that calculation. I guess this probably should be in your tutorial as well. This is a very simple calculation. You already did the calculation, just the conversion that you need. And so if you do this calculation and find the current estimate, find an age for the universe, you will get very close value. And the value that you would get is roughly 13.9 billion light years, right? And so I have not put the answer here, so I will leave that for you to work out the problem and find the answer, right? So this should be also in your tutorial as well. And the current estimate that we have as the age of the universe from different experiments is that 13.7 billion years, right? So that is the idea. So we have an estimate like 13.7 billion years. And so that is very close to the value that we calculate in this problem, assuming an expanding universe, right? Now, and also I have asked you to comment on the current estimate of the age of the universe compared with your answer, right? So you can do that as well. So what that means is, if you do the calculation assuming an expansion universe, so you will get an answer very close to about 13.9 billion light years. The actual estimate for the age of the universe is 13.7 billion light years, right? So what that means is those two numbers are very close, right? So you need to think about why those two are very close, right? So we are making an assumption here to solve the problem like that. The universe, the expansion of the universe has been a constant, and it seems like it is a constant for a long time, right? So that is the assumption that we made, and with the calculation, and when you compare that calculation with the actual age, those two are very close. So what that means, our assumption is reasonably correct, right? So that is the idea. The expansion of the universe has been a constant for a long time. So that's why two answers seems to be close to each other, but it is not a constant for the whole period. So there is a era where you have something called inflationary universe, that you have sudden expansion and then it became a constant for a long time, and now it's accelerating. But we will discuss those things. But the idea here is, assumption that you made as the velocities are constant, velocities are constant, seems to be reasonably correct, right? There are small deviations, but still it is a good approximation to find the age of the universe, right? So that's all that I would like to discuss about the Hubble parameter and Hubble law based on these equations that we have for the proper distance, which we started to derive from the the Robertson-Walker metric. And now let's move on to Friedman equations, right? Now these Friedman equations are derived using the Robertson-Walker metric. The Robertson-Walker metric is the metric that explains the homogeneous and isotropic universe, or the metric that satisfies the cosmological principle, right? So what we need to do as the next step is to guess, to have an educated guess about the energy momentum tensor that describe the flow of energy and momentum in this large scale structure of the universe, right? Now, if you remember about the chapter that we talked about the Schwarzschild metric, we did the same thing, right? So we have a metric. So once you have the metric defined, you can find the connection coefficients and then Riemann curvature tensor, Ricci tensor, and the Ricci scalar. And from that, you can complete the left-hand side of the Einstein's field equation, right? But for the right-hand side, you should have a source of this energy. So that is basically given from this energy momentum tensor, right? Now, in here also, it is the same case. Once you have the metric defined, the procedure is straightforward. You need to find the connection coefficients and then Riemann curvature tensor and the Ricci tensor, which will go into the left-hand side or one of the sides of the field equation, right? And the other side, you need to find the energy momentum tensor, right? And before we move on to the field, plugging these values into the field equation, let's look at the energy momentum tensor, because you need that part as well, right? Now, cosmologists actually assume make some of the assumptions in this case. Now, the first one is they assume that the universe can be treated as a perfect fluid that characterized by proper density and proper pressure, right? So they assume that a universe can be treated as a perfect fluid that characterized by the proper density and proper pressure. So this is the same, which is somewhat similar to what we have discussed under Schwarzschild metric. Now, a fundamental observer that travels with this cosmic fluid can be described by an energy momentum tensor of a perfect fluid, right? Because of that, we can, if there is an observer that travels with this particular cosmic fluid, it can be described by an energy momentum tensor of a perfect fluid, right, in a momentary co-moving reference frame. And we have met this this tensor earlier, so that is T mu nu, and this first term is where you have the density, and then the other one is the pressure, right? Other three terms are pressure. So I hope you are familiar with this particular tensor. And then in this particular situation, according to the knowledge that we have now, this cosmic fluid can be treated as a mixture of three components, right? And those three components are matter, radiation, and the source of dark energy. So those are the three main components that we believe that this perfect fluid consists of, right? And because of that, if you take each of these terms, the first one is, the density, and the other two terms are pressure terms, right? Now this density, or the proper density, is a combination of matter density, radiation density, and the density comes from the dark energy, right? Once again, the density consists of three main parts: matter density, radiation, and the dark energy. It is the same for the pressure. It will be again the pressure coming from the matter, and then pressure from the radiation, and the pressure due to the dark energy source. And so there are basically three main components that you have to consider here: matter, radiation, and dark energy. Now, when you say matter, the dark matter is also included inside that. Right? So that is something that you have to make sure that you understand. Right? Dark energy is something else. Right? So that is the important point here. So you may have the question in your mind that isn't that you cannot convert dark matter into dark energy, but that is not wrong. That is not correct, right? Here, the way that they use this term matter and energy is different than what we used to see, right? The dark matter is something, a type of matter that you cannot see it, but you know that it gives you a gravitational attractive influence, right? So that is dark matter. And the dark energy is something that is giving you a repulsive force. So that's why dark energy is responsible for accelerating universe, right? So dark energy is kind of, you can actually think that as a source of like an anti-gravity, right? Not gravity. So that is the difference between the dark matter and dark energy. So make sure that you have that in your mind, right? Sometimes you may get confused with those two terms. Right. Now, to look at this dark energy, since we haven't met it before, let's consider this equation, which is the modified Einstein field equation, right? So we have discussed this earlier. So I have written the same equation here. And then this is this dark energy term, or the cosmological constant in Einstein's modified equation. But remember that at that time, Einstein did not put this constant to represent the dark energy, right? So he had an idea that our universe should be static, and because of that, you should have a term right here to stop this expansion, right? So that's what he did. But now we know that this is the dark energy term. So that is the current usage of that. And if you keep these two terms in the left-hand side of the equation and take this term to the right-hand side and take the kappa out from the, so let's say K here, just to make it easy, K out from the, not K actually, because we have a K later, so let's put that as kappa and take out from the brackets. You can write an expression right here in the right-hand side. And we know that what is T mu nu, that is the normal energy momentum. And then the term or the energy momentum that comes due to the dark energy, you can actually represent it in this way, T bar mu nu, right? So that is, take that as a dark energy component from its own energy momentum tensor component, right? And that value of this T bar mu nu is given here. So that is basically this term right here, right? So we just put a name there just to identify it easy, right? Now you can see that in the Einstein's equation, you have the curvature terms on the left-hand side, and then on the right-hand side, you have the normal energy momentum and the source of dark energy right here, T bar mu nu. So that's what I have done here. And so my aim is to show you how this dark energy term looks like at the end. And now if we assume that we don't know actually much about the dark energy, but if we assume that the source of dark energy, whatever the source of dark energy component, can be treated as a perfect fluid with pressure P lambda and density rho lambda. We have actually used these two terms earlier as well. We can write this energy momentum tensor in this way, like in this equation 26. Right? Now, the reason that I can write it in this way is, if you recall the energy momentum tensor for an ideal fluid that we have, written earlier chapters, especially in, I guess, in lecture 6, we wrote it in this way: T mu nu equal this whole term, and we are going to. I have basically used the same equation right here. The only difference is now in terms of rho, you have rho lambda. So that's for the dark energy term, and for the pressure, it will be P lambda. And then in terms of P here, you have P lambda, right? So I have written the dark energy term in that way. However, I know that this whole expression should be equal to this value right here, right? So that's what I have defined as the T bar mu nu term. So I basically equate those two, right, in equation 26. And now from equation 26, if you take the coefficients of G mu nu, on the left hand side, you have a coefficient that is lambda over K. On the right hand side, on the left hand side, for the coefficient as the coefficient of G mu nu, you have P lambda right here. And in fact, it's minus P lambda. So that means that this P lambda should be equal to minus lambda over K. So if we are comparing coefficients in this equation, right? And that's what you have here. Not K actually, this should be kappa. And the other term that you have in the left hand side, this U mu U nu term, that term is rho lambda plus P lambda over C square, right? However, in the right hand side, you do not have that term. So which means the U mu U nu term, there is no term in the right hand side. So that means that particular term should be equal to 0, right? So that means this term P lambda over C squared plus rho lambda should be equal to 0, which will lead to this particular equation P rho lambda. So that is the density, and P lambda is the pressure, and there is a relation between those two. And this C is the speed of light, and I believe that it should be simple as well. Right. So let me. And there are some, so let me just make that correction straight. C squared. Right. So I just did some, corrections for the terms. Right now, if you look at these two expressions, 27 and 28, this will give you P lambda, rho lambda equal P lambda over C squared. And then this P lambda can be written as minus lambda over K from 27. So that will give you the minus that you have already here. So that new minus sign will cancel out. So you have lambda squared over C squared kappa. Right? And this value of kappa K is given as, I don't know whether I have here, but you should have the previous knowledge about. Yes, I have not mentioned here, but if you go back and look at your notes, no, let me put it in this way. Yes, let me open up the previous. We have the previous lectures. Right, so I guess lambda has not defined here. Right, but you can see that the kappa is defined here, the Einstein constant, right? It should be 85G over C squared. So that's what I want to make sure. Right, now if I go back, right here, so the kappa is substitute here as 85G over C squared. So that's how you get this whole expression at the end, equation 29. And now from these two equations, 27 and 29, you have P lambda equal minus lambda over kappa. And then yes, the lambda it should be equal to rho lambda C squared K kappa. And I think you can combine all these things to get this equation, right? So it is not that much hard. And what is important here is this tells us something important about the dark energy. So that means the positive dark energy density rho lambda results in negative dark energy PA, right? So when dark energy pressure, if the pressure is positive, then the density is negative. So it goes in, vice versa like that. And so just to make sure this should be, yes. So that's the idea. A positive dark energy density rho lambda results in a negative dark energy pressure PA, P lambda. Right? When one is positive, the other one is negative. Right? And this tells us something important thing, that is the dark energy component precisely represents the effect of the cosmological constant. And at the same time, because the effect of cosmological constant is we have a accelerating universe, which means the force or the effect should be completely opposite compared to the gravity. Gravity is attractive. If you have a gravitational effect, then this should not contribute to the accelerating universe, right? So that is the idea. So the contribution of the dark energy will lead to large scale repulsion, which is kind of an anti-gravity. Let me see, there's a spelling mistake here. Right. So that is important here, right? So the dark energy contribution will lead to large scale repulsion, which is a kind of anti-gravity, right? So that's what normally called as an anti-gravity. And however, we only know little about the dark energy. What we know is this accounts for 70% of the total energy of the universe, by the way, right? So that is the mystery that we have. We don't know much about this dark energy, which is normally account for the 70% of the total energy of the universe, right? And we also don't know much about the dark matter, which is again a considerable amount. So when you consider all these facts, we will only know about a very, very small amount about the universe, around like 5% of the matter, right? And you will get into know about these details when you read about the last chapter, right? So that's why it is there, right? So that's about some more information about the dark energy. Now let's go back and look at these density and pressure terms that we have been discussing. Now, another assumption that cosmologists make is that the matter component of the universe, normally the matter component means all the matter in stars, galaxies, and also in dark matter, right? Dark matter also a matter component. Remember once again that this dark matter is not related to the dark energy part. It's a completely different thing, right? And so this, matter component normally related to stars, galaxies, and dark matter. And the cosmologists assume that it has a zero pressure, right? So that means you can directly write that PM T, which is the proper pressure, as zero, right? And another way, this means that the matter component of the universe can be treated as a dust, right? I think we have discussed this earlier in the chapter about the Einstein's equation, right? So that's why I'm not going to discuss much into details here. And now this will leave us with two pressure components and three density components in equation 21 and 22, right? So that means for the matter component of the universe, we assume that we don't have any pressure, so there will be zero pressure for the matter component. What that means is, if you go back to 21 and 22, so that is the proper density is given as the matter density, radiation density, and the dark energy, the density from the dark energy source. But that's okay. You can keep it like that. But for the pressure, it's again coming from the matter, radiation, and the dark energy. And out of those three parts, the pressure is the pressure due to the matter is assumed to be zero, right? Because we normally assume it as a dust or the matter. So it means the pressure from the matter will be assumed as zero. So that is why I used to tell that there are only three components of densities and two components of pressure. Right, let me go back here. So that's why I have mentioned here two pressure components, radiation and dark energy component, three density components. So that means all three matter, radiation, and dark energy. Right, now let's look at how these different quantities, matter, radiation, and dark energy, so they change with the time, right? Now, if you consider a cube that contains a matter and radiation, think that you have a container that has both matter and radiation. And if you increase the length of a side of that particular cube by let's say twice, what will happen is, 2 times 2 times 2, the volume will increase by a factor of 8, right? So if you think it in similar way, what will happen to this matter density is, so once what will happen is, for the density, when the volume increase, density will decrease, right? And because of that, you can write that the matter density will be proportional to 1 over r to the power 3, where r is this scaling factor, right? The value of the scaling factor at that particular time. So once again, when the volume increases, let's say twice, then your increase of the volume will be 2 to the power 3. So what that means is, this always the matter density decreases with this scaling factor, which that means when you increase the size, and that the relation is, it is inversely proportional to the r to the power 3. So that's what happened to matter density. Now, if you look at the radiation density normally given in terms of E equal HF equation, where you can easily see that the energy is inversely proportional to the wavelength. Now, what would happen in the similar situation, when you increase the volume by double, the wavelength will also double, right? Now, what will happen is, in addition to what this relationship, that increase of the wavelength will again decrease the energy. And because there is an additional term that comes from the wavelength, the radiation density will be inversely proportional to r to the power 4. Right? You can see the difference. The matter density it's also decreasing with the increasing scaling factor. However, the decrease of the radiation density is even larger, right? So what this means is that for an expanding universe, density of radiation will decline more rapidly compared to the density of matter, right? So as you can see, that the matter density, it goes like 1 over r to the power 3, and the radiation density that goes from 1 over r to the power 4, right? So those are two different relations. And you can see when r, or the scaling factor, increases gradually, the radiation density that goes like 1 over r to the power 4 will quickly decline compared to the matter density, right? And in fact, this is what has happened to our universe according to the Big Bang theory. And remember that we only discuss here matter and radiation densities. There is this dark matter the dark energy term, which is we normally consider that as a constant with time, right? And because of that, but there is something that I have to check here. This should be dark energy. Yes, this should be dark matter density. No, it should be dark energy density. Let me do that correction. It should be dark. So the dark energy density is considered as a constant with time, right? Because dark matter is included already in the matter part, right? So you don't have to consider that separately. And this graph nicely explains what has happened since the Big Bang. So let's say this is the time place where the cosmic time started, and you measure up, let's say, up to now. And here is the energy density contribution from all three parts: matter, radiation, and dark energy. And you can see that initially up to a certain point, let's say if you take this particular dashed line up to that particular point, this red curve is higher than the blue curve. The red curve is the one that shows you radiation is proportional to 1 over r to the power 4. For smaller values, the radiation density is higher in the universe, right? However, after a certain point, it is this first dashed line right here, then the matter density takes over and the radiation density drops, right? And it has continued like that for a long time. And then there is a time that both radiation density has already gone down and the matter density also gone down compared to the dark energy term or dark energy density. You can see that the dark energy density is constant, right? It does not change with the time. So that's why you have a horizontal green line here. Now up to this particular point, it is the matter that was dominating after the radiation. Up to this particular point, radiation density is dominating, and after that point up to here, matter was dominating the universe. And then after this particular point, matter continues to go down, but however, the dark energy term is there, right? And because of that, the dark energy will be dominant in this particular era after this particular point. So I have not mentioned the times exactly, but that's what happened. So initially we had the radiation dominance universe, and then we had the matter dominating universe. Now we are in a dark energy dominating universe, right? So those are the three scenarios, right? And we have explained mathematically here why is that based on the scaling parameter, right? Right. And then I think, is there any, right? So let me at least finish up to this particular point so that basically we can directly talk about the different models from the Friedman equation on the next day. Now, if you consider the present time, you can tell, let's say, t equals 0 as the present time. And if you take the matter density, it can be at present time, that matter density can be written as rho m0. What that means is the matter density right now. And let's get the scaling factor RT equal to R naught right now. And then after a time t equal t, the matter density will be rho mt because it is a function of time, right? So it is changes with the time. And let's take the scaling factor as RT, which is a function of time again. Now, what we know is the matter density is proportional to the third R to the power 3 at any particular time. And if you look at the matter density right now, that will be inversely proportional to the scaling factor right now, which is given from R naught, right? And from this relation about the R naught, you can, I mean, you can think, if you think about carefully, you can really write it. That is the matter density function, which is a function of time, can be written as the matter density right now times R naught, which is the scaling factor, to the power 3 divided by R to the power t to the power 3. Right? I guess you can get this relation easy, right? This is like coming from the A-level physics. And similarly, you can do the same thing for the radiation density, rho RT. So that is the radiation density right now. And then the rest of the part as a function of the scaling factor now divided by the scaling factor as a function of time and the fourth power of the whole thing, right? So you can write it in this way because, I mean, the reason that I am, doing all these things, we are going to have the Friedman equations as the next step, and then going to, discuss different models about the universe, right? So those models, when you discuss those models, these things will come into play. So that's why I am going to discuss about this matter density and the radiation density and the dark energy today, so that I am going to use it in these different models at under different conditions, right? And which means now I have an expression for the radiation density as a function of time and for the matter density as well. Now I can go back to this equation, which is this one, right? And substitute values for rho mt and rho RT, which is what I am doing here, right? Because rho mt is, rho m0 times R naught over R to the power 3, this expression right here, you can plug that here. And then similarly for the radiation density, since the dark energy source is a constant, you don't have to plug anything, so it will be appear here as a constant, right? It is not a function of time. Now this is for the density. Now if you look at the pressure equation about the cosmic pressure changes, we can actually do a simplification based on this equation of state. Now this one you probably have not heard it. This is the equation of state related to the cosmology, and that this basically relates pressure and the density with this omega parameter, and this parameter can take three values. If this this is dust, then this omega parameter will be 0. So that means basically the pressure will be also 0, right? P equals 0 times rho c squared. If this is radiation, then this parameter omega will be equal to 1 over 3, and you can directly plug it value 1 over 3 times rho c squared. So that is the radiation term, and for the dark energy it is -1. So that will be minus rho c squared, right? And if you take all these three components, then your cosmic pressure equation will become, the matter part will go away, because we know that when omega equals 0, the pressure, it is dust. So that means the pressure will be equal to 0, and then you can write the radiation part plus the dark energy term, right? Which will give you a new equation from the pressure that is derived based on this equation, which is the equation of state for the cosmology, and these three parameters that omega can take, and combining all these three things with the equation 21, 22 is right here. That is this equation. Right? So this first term will be 0, and you have a second term and the third term there. You will get this equation right here. Right? Now the idea is, you can see that all of them are, functions of time. Pressure is function of time, and then the density is also the same in equation 35 and 37. The advantage here is, you can see that in both these equations, if you know these two factors, rho r0, which is the radiation density right now, which is probably what you can measure, right? From an experiment, you can measure what is right now there, and then the scaling factor, right? And that in a particular time, and the scaling factor right now, you are done with this pressure, right? You can directly calculate it. And it is the same for the density as well. And that's what I have written here. If cosmologists know the three factors, matter, radiation, and dark energy densities in a certain cosmic time, at any time, let's say the time right now, then, and the scaling factor, RT, right? Scaling factor at a particular, how the scaling factor changes, then they can calculate the cosmic density and pressure at any other time. So that is the advantage. So if you know these values, you can actually calculate the cosmic pressure and density at any time. And the idea is these two relationships we will use in the next section, where I am going to derive the Friedmann equations, right? Right. So I guess now we have all the background that we want to discuss about the Friedmann equations, which are the equations that are basically used to model the universe, right? And so if you can see the left hand side, so I have a table of content here. So we are right here talking about the cosmic energy, momentum, density, and pressure, like that. And then the next day I am going to start talking about the Friedmann equations. That is this section, right? Instead of deriving these Friedmann equations, I am going to tell you how to do it. But if anybody needs to derive it, you just need to start from the metric, find the connection coefficients, Riemann curvature tensor, Ricci tensor, and Ricci scalar, so that you can plug all these things into the left-hand side. In the right-hand side, you have to use the energy momentum tensor that we have just discussed, right? So that's how you have plugged everything into the Einstein's field equation in this particular situation, and then you have to solve the field equation to get these two differential equations, right? So those are the two equations that we call as Friedmann equations. One is actually called the Friedmann equation, and the other one is called Friedmann acceleration equations. So I'm going to discuss those two equations on the next day, and the different models that we can talk about, depending on different values. And actually some of these models will be not realistic, and even, you can't even think about having a model like that right now. But the idea is, I just want to give you an idea how astronomers build these models, and then how to look at those kind of things in the most simple way. So because of that, I have chosen the same models that are discussed in the book, which are very simple to understand, and you can also get the basic idea, right? So we will not go into discuss about very complex models, but as an initial point, we will discuss these things. And also we have to discuss what is the currently accepted universe for us. So that will be the last section in this particular lecture. So hopefully I expect that we will be able to finish on next Monday, at least Monday or Tuesday. I will let you know. It will be most probably on the Monday evening, so that I can finish all these lectures that I have to do in this month, so that we can start talking about the tutorials in the within the next 2 weeks. So I will start from the beginning with the first tutorials about the astronomy, and then we'll discuss all these tutorials. And at the same time, I will try to, revise what we have done at least a little, so that we can go to the notes and look at those. Because this course now have been teaching, for I guess 8-9 months. So it's easy to forget things, right? Right. So anybody have any questions? Oh, by the way, if anybody is familiar with, this Jupyter notebook, and if you need the note in that format, if anybody needs, I mean, I don't mind giving it, right? So, because I used to upload the HTML, either HTML or the PDF version of this to the LMS. But if anybody would like to have, this table of content and everything in the same format, so this particular file I can give to you if anybody is interested, right? So let me know if you need, right? Any questions up here?